Well, now let's analyze a slightly more difficult circuit and get the RC time constant for this one. We have not a very complex circuit. It looks pretty simple, but here's the RC part that we've already analyzed. But of course, this branch is in parallel with this 12 ohm, which is in series with this one. So it's going to change things. Let's see how that works. Well, we have I1 through here. We can call this branch I2, and then this is going to be I1 minus I2. So we really only have two currents to worry about here. Now, just looking at this from the broadest point of view, initially, when we start, the capacitor looks like a short circuit. It acts as though it's just a wire connected across here. So this circuit is just a series parallel. Two 12s in parallel make 6. 6 in series with 12 is 18. So it's initially just a 18 ohm, like an 18 ohm resistor. And then as time goes on and the charge builds up across here, this eventually looks like an open circuit. So it's almost like you could take this branch and throw it away. And we have 12 in series with 12, which is 24. So it goes from 18 to 24 ohms from the point of view of the source. Then what we're really interested in is, these three currents, I2, because I2 is the one that's being caused to vary as a result of this capacitor being charged, as we've already analyzed. So we'll want to focus on I2. But considering that as this goes down, then it's drawn less current from the source because this branch is drawn less current, and thus the voltage drop across here goes down. So it's a relatively complex interplay. As we diminish the current over here, this whole resistance goes up, which reduces the voltage drop across here, and therefore there's more voltage available across this whole thing, which is across this 12 and this combination. So you feel confused yet? Well, let's just take it a step at a time here, and it won't be so hard. So in each path, R is 12 ohms, just to make things simple. So at t is equal to 0, I already mentioned, the initial current is V over R, the EMF over R, total, which is 12 over 18, or 0.67 amps. That's easy. That is from the point of view of the source. Now later, much later, steady state conditions, t is equal to infinity, that current is going to be based on not this side, because this is open, no current flowing over here, just these two in series. 12 over 24, half an amp. So we can actually graph the current at this point. The current in the circuit varies between the initial and the steady state, and it looks like this. So that is graphing the current from the point of view of the source, not over here on this branch. We'll figure that out momentarily. Let's do a Kirchhoff loop. We're going to actually need a couple. We have two unknown currents. So let's get two equations. This is going to be my first loop, the left-hand one here, going clockwise. And that looks like EMF minus I1R, and we'll just call the 12 ohm R because they're all the same thing, minus IR. That's I1R, but then there's also I2. And since it's minus, we go plus I2R equals 0. And the second loop I'm going to use is around the entire thing. Let's start with the EMF again. Minus I1R, minus I2R, and then the voltage across the capacitor, Q over C, equals 0. Now, of course, we want to combine these two equations to get rid of one of the variables, and the variable we're most interested in is I2 because that's where the capacitor is. So to get rid of I1, we'll multiply equation 2 by negative 2, and so here's equation 1 again, simplified, and equation 2 minus 2 EMF plus 2 I1R plus 2 I2R plus 2Q over C equals 0. These we're going to add, and when we add these together, we get minus EMF. The I1s go away, which is what we wanted. We have 3 I2R plus 2Q over C equals 0. So this is going to enable us to get a differential equation, because I2 is what we're interested in, and it's related to this Q. The Q is the charge on the capacitor, and it's a direct consequence or relation with the current in that branch. So let's analyze that equation. Okay, it's time to do the math. So a quick rearrangement gives us 3I2R equals EMF minus 2Q over C. Now, I2 is dQ dt, and again, as I mentioned, this I and Q are related. The Q is based on the current flow, so that's good. So dQ dtR equals EMF minus 2Q over C. Multiply the EMF by C over C, and then we can express it as like that. And now we have the 3 over R, so to get dQ dt by itself, let's divide by 3R, and we get EC minus 2Q over 3RC. Recognizing, hopefully, that this Q over here, we got a Q here, so we have to separate the variables, bring this down here, which is what I just did. And that gives us our differential equation to solve. That looks familiar, doesn't it? We've done this kind of thing before, so let's just continue the math here. Integrate both sides. There we go. And on the left-hand side here, we have a natural log function. dq, here's a q. So let's do it. Natural log of EC minus 2Q, and then multiplied by, or divided by, the negative 2. So here we are, and we can easily just multiply by 2 to simplify this left side a little bit. Actually by negative 2. There it is. And now let's write that as follows. Natural log, it's the ratio of that difference there, equals minus 2 over 3RCT. Almost done. Let's E both sides. There we go. And we get EC minus 2Q over EC, e to the minus T over 3 halves RC. And you're now seeing something that pertains to the time constant, which is one of the things we're trying to find here. Well, as you look at this, the charge should emerge from this. So this is 1 minus 2Q over EC equals e to the minus T over 3 halves RC. And let's get the Q by itself. So 1 minus that term. And finally, the charge, the time-dependent charge, is 1/2 of E times C, right? So EC is Q, the maximum Q, but it's only half. You can think of it as follows, that in the end, we only have half of the voltage, EMF over 2, across that leg with the RC leg that's in question. After a long period of time, you got a 12 ohm that the source sees first, I'll say, even though the source doesn't see any particular component first. But you got the 12 ohm in series with that whole right branch, which now looks like just another 12 ohm. So EMF over 2 is the ending voltage across that RC branch. And otherwise it looks very much the same. But remember, we talked about an RC time constant. There's RC sitting here. Well, now there's 3 halves sitting there. So the time constant is 3 halves RC. And we've just had a lot of fun analyzing a slightly more difficult RC circuit. For the most part in AP Physics, you won't have to deal with something this difficult, but occasionally. Usually it's just a simple RC. And making sure you got that nailed down solidly, which I hope you do at this point. And that will conclude our RC circuit analysis, at least for now.